Yes, so now we have completed the introduction part in the last video. So now we will continue with the first main part of this book, which has some basic maths required to understand the rest of the main content of this book, and also some machine learning basics. Now again, like I said in the last video, this series of videos is basically me trying to revise the book, and if you guys find it helpful, it is an added bonus. And uh, yeah, so I'll try to explain things as much as possible, but you must also know that I'm trying to revise the concepts, and I'm not really fully prepared as a teacher. So this is not a lecture video in the traditional sense. So coming to the first chapter here, we have linear algebra, and so here they have explained the basic meaning of scalars, vectors, matrices, and tensors. Now you must know that the tensor is basically the most fundamental concept here. So a tensor is just an array of numbers arranged on a regular grid with variable number of axes. So basically, a tensor with just a one dimension or just one number is called a scalar, and a tensor with a series of numbers and which is just one dimension is called a vector, and tensor of two dimensions is called a matrix, and a tensor of I dimensions can be called as a tensor of I dimensions. Let's say a tensor of three dimensions we can denote as tensor of three dimensions like x, y, z, and maybe an element inside that three-dimensional tensor at coordinates I, j, and k can be denoted like this. So, and another basic idea is the transpose of a matrix. So a transpose is basically take like a matrix like this, and you switch it like this. So that is the basic idea of a transpose. So and so the next section is the multiplying matrices and vectors. So here we are just showing how we multiply matrices and vectors. So matrix multiplication is distributive. It's also associative, and the dot product between two vectors is commutative, and the transpose of a matrix, the transpose of two matrices is equal to the transpose of the individual matrices, but in the reverse order, as you can see. And of course, if you apply transpose two times, you will get the same matrix. Transpose of a matrix is just the original matrix itself. So these are all basic concepts, and identity and inverse matrices. So an identity matrix is just a matrix which has one along the dimensions of it. Like this, this is an identity matrix of dimensions 3 into 3. So 3 times 3. So it has 1 along the dimension and 0 in all other places. So that would be an identity matrix, and the matrix inverse would be like this. So an inverse of a matrix exists only if it satisfies this equation. So, and finding an inverse is not that easy. So I would highly recommend trying to go through the linear algebra textbooks, and that is a better way to learn about it. So now going to the next topic, linear dependence and span. So what's a linear dependence really? So let's go through this topic, and it's been quite some time, and I might have forgotten the concept here. So In order for A inverse to exist, the equation must have exactly one solution for every value of B. System of equations to have no solution or infinitely many solutions for some values of B. It's not possible to have more than one, but less than infinitely many solutions for particular B. Yeah, so solutions equation has anything columns. Specify determine how many B in this field. The each element specifies how far we should travel in each of these directions. Yeah, so linear combination is another important topic in linear algebra. So formally, a linear combination of some set of vectors is given the multiplying each vector corresponding scalar coefficient and then adding results. And the span of a set of vectors is a set of all points obtained by linear combination of the original vectors. Now, I highly recommend you guys to look up the channel 3 Blue 1 Brown by some guy. I forgot his name, but it's a YouTube channel, and it's he does an amazing job of visualizing these linear algebra topics. So there's a whole playlist of linear algebra by him, and 3 Blue 1 Brown. So that's the channel. So please refer that one. So a span is basically a set of all the possible points obtained by the linear combination of the original vectors. So linear combination is basically like let's say like y equals like mx plus c. So this would be a linear combination, but there's only one x1. Let's say so there's only one variable, and we have only one coefficient, and this is a scalar. So scalar coefficient, and yeah, so this would be a linear combination. Some vectors is given multiplying each vector because of the coefficient and adding the results. So the sum of all of that would be a linear combination, and then the span of a set of vectors is the set of all points obtained by linear combination of the original vectors. Yeah. So let's just try to go through this again, just to try to understand it a little better, because some of these concepts are would be really important. So in order for inverse to exist, equation 2.11 should be ax equal to b must have exactly one solution for every value of b. The value of b, this equation must have only one solution in order for A inverse to exist. However, it's possible that for the system of equations to have no solutions or infinitely many solutions for the some values of b. It's not possible to have more than one, but less than infinitely many solutions for a particular value of b. So both x and y are solutions, then z equals alpha x plus 1 minus alpha y. So is also a solution for any real alpha. To analyze how many solutions the equation has, we can think of the columns of A specifying different directions we can travel from origin. Point specified with and determine how many ways there are of reaching B. A as specifying different directions we can travel from the origin. You can think of columns of A as specifying different directions traveled from the origin. And how many ways of that to reaching B? In this view, each element of X specifies how far we should travel in each of the directions, with the xi specifying how far to move in that direction of column I. Yeah, so that's one way to explain it. In general, this kind of operation is called a linear combination. Formally, there is a linear combination of some set of vectors is given by multiplying each vector by the corresponding scalar coefficient and adding the results. So a span is basically a set of all the values. So determining whether A could be the solution amounts to testing whether B is the span of columns of A. This particular span is known as the column space or the range of A. So he also explained the concepts of linear dependence and linear independence, and it would be better to go through this in that channel. Like I said, 3B1 Brown, and try to understand. Let's try to skim through this concept, which is the whole idea of this series of videos. Formally, this kind of redundancy is known as linear dependence. So, what is exactly linear dependency? Having okay, plus immediately must have columns, otherwise the dimension need to be less than consider 3 times 2 matrix 3D, but modifying whether from set of vectors is linearly independent if no vector in the set is a linear combination of other vectors. Yeah. So note that the requirement is for a set of to have exactly m linear independent columns, not at least m. Linear, so a square matrix. So the matrix must be a square, and a square matrix with linearly dependent columns is known as singular matrix. If A is neither not square or is square but singular, it can be still possible to solve the equation. However, is the methods of we cannot use the method of matrix inversion to find solution. Inverse is being multiplied on the left. It's also possible to inverse on the right as well. So the square matrix of the left and right inverse are equal. Norms. Now, so let's go through the concept of norms. Now, sometimes we need to measure the size of a vector. And so norm is basically the size of the vector, and it's noted like this. In machine learning, we usually measure the size of the vectors using a function called norm. So this function will be available in a lot of Python packages and in other languages as well. Formally, LP norm is given by, so this is the LP norm. It means LP. So LP norm is given like this. So basically, sum of all the absolute values of vector powered to P from I to, and then you are taking the root of it. Norms including LP norm are functions mapping vectors to non-negative values. Intuitive, the norm of vector measures the distance from the origin to the point x. Molecular norm is any function that has satisfies following properties. So function is 0 only if x equals 0, and if of x plus y always less than or equal to f of x plus f of y. Also called the triangle inequality. Now remember this concept because it also comes back in the idea of artificial intelligence. So triangle inequality concept comes in there's a certain concept where this is applied. Yeah, so triangle inequality comes in the concept of admissibility and consistency of an algorithm of a heuristic in the artificial intelligence subject. So anyway, so now going to L2 norm, if P equals 2 is not the Euclidean norm, and it's simply the Euclidean distance from the origin to the point, and L2 norm is frequent machine learning is denoted by x bar. So if you see x with 2 bars like this, x norm, that would be L2 norm, also known as Euclidean norm, with the subscript 2 omitted. So we omit the subscript 2. Common measure size of vector using squared L2 norm, which is denoted simply as x transpose x. The squared L2 norm is more convenient to work with mathematically and computationally than the L2 norm itself. For example, the derivatives of the squared L2 norm with respect to each element depend only on the corresponding element of x, while all the derivatives of the L2 norm depend on the entire vector. In many contexts, the squared L2 norm may be undesirable because it increases very slowly near the origin. In several machine learning applications, it is important to discriminate between elements that are exactly 0 and elements that are small but non-zero. In this case, we turn to a function that grows at the same rate in all locations but retains mathematical simplicity, the L1 norm. L1 norm is also called as the Manhattan distance, or I may be wrong, or I think I'm right. So L1 norm is the Manhattan distance, which is just the sum of all the absolute values. One of the elements in machine learning, the difference between 0 and another element is very important. Every time an element of x moves away from 0, epsilon L1 number increases by epsilon. We sometimes measure the size of the vector by counting its number of non-zero elements. Some of authors use the L0 norm. So L0 norm is to measure the size of the vector by counting its number of non-zero elements. This is also called as the L0 norm, but this is incorrect terminology. Non-zero entry is not a norm. So because scaling a vector by alpha does not change the number of non-zero entries. So the L1 norm is often used as a substitute for the number of larger entities. So one other norm that commonly arises in machine learning is the L infinity norm, also known as the max norm. This norm implies this simplifies the absolute value of the element with the largest magnitude of the vector. So yeah, that would be the max norm. Sometimes also we measure the size of the matrix in context of deep learning. The most common way to do this is the otherwise obscure Frobenius norm. So yeah, it's quite unique. It's an analogous to the L2 norm of a vector. Dot product of two vectors written in terms of norms. Yeah. So you can also find the dot product using the norms. So going to the next one, special kinds of matrices and vectors. Some special kinds of matrices and vectors are useful. Diagonal matrices are mostly of zeros and have non-zero entries only along the main diagonal. And as the description goes, a diagonal matrix is basically an identity matrix times a scalar. So symmetry matrix is any matrix whose transpose is equal to itself. Unit matrix is a vector with unit norm. So unit matrix doesn't mean that the number of elements is just one. So that's how to. So the norm should be one. So that's a condition for a unit matrix for a unit vector. So unit vector is a vector with just a unit norm. So a vector is called orthogonal to each other if x transpose y is zero. If both have a non-zero norm, this means that they are at 90 degrees to each other. Vectors are not only orthogonal but also have a unit norm. So unit vectors which are also orthogonal are called as orthonormal. So that's familiar to me. An orthogonal matrix is square matrix whose rows are mutually orthonormal and whose columns are mutually orthonormal. So in which case A inverse will be equal to transpose of A. Now coming to eigen decomposition. So here, as you can see in this equation, A, V, where V is an eigenvector and A is a square matrix of non-zero. The non okay, an eigenvector of square matrix A, the non-zero vector V. So V is the non-zero vector. A is just a square matrix, and V is the eigenvector, such that multiplication by alters only the scale of V. So multiplication by A alters only the scale of V, the non-zero vector V. Eigenvector of a square matrix A. So A is the vector to which we are finding the eigen. A is a square matrix for which we are finding the eigenvector, such that multiplication by A alters only the scale of V. So only the scale of V keeps changing, and by multiplication of A. So when vectors, when a non-zero vector's scale changes, and only that is what happens when you multiply it with some, let's say, square matrix A, then that non-zero vector is called the eigenvector of that matrix. So now you can find the eigenvalue from this eigenvector with this equation. The scalar lambda is known as eigenvalue corresponding to the eigenvector. One can find a left eigenvector such that V transpose A equals lambda V transpose, but we usually concern with the right eigenvector. So if V is an eigenvector of A, then there is a scalar vector of SV. However, still has the same eigenvalue. For this reason, we usually look for the eigenvectors. So again, we are going to skim these concepts. I'll cover the mathematics in a separate series. Here we're mainly in this series of videos we will mainly cover the deep learning concepts. Suppose that a matrix has linearly independent eigenvectors with the corresponding balance. We concatenate all the eigenvectors. Yeah, single value decomposition. So SVD, also called as SVD, the more Penrose pseudo inverse. So sometimes trying to find an inverse can be computationally very expensive, in which case we can try to find a pseudo inverse, so which is called as a more Penrose pseudo inverse. Matrix inversion is not different from matrices that are not square. So yeah, this is also for the matrices which are not square. Suppose we want to make the left inverse be for matrices, so that we can solve it in an equation. F multiplying is depending on the structure of the problem, it may not be possible to design a unique point from A to B. The phase taller and B, then it is wide. Also for this equation to have no solution. The phase wider than just all and multiple solutions. So the more Penrose pseudo inverse allows us to make some headway. In this case, the pseudo inverse of A is defined as matrix A plus A equals limit alpha tends to 0 of A transpose times A plus alpha times inverse alpha times an identity matrix, and you take the inverse of this whole thing and then multiply it with the transpose of A. Practical algorithms for computing the pseudo inverse are not based on this definition, but rather the formula A pseudo inverse equals V times D pseudo inverse into transpose of U, where UDV are singular value decompositions of A, and the pseudo inverse D plus is the diagonal matrix D is obtained by taking the reciprocal of its own non-zero elements, then taking the transpose of the resulting matrix. When A has more columns than rows, the summary equation is in the reverse solves many problem solutions, which will provide solution to matrix normal possible. When A has more rows and columns, possible for there to be no solution. So the inverse gives the x for which is close equal to the clear norm. The trace operator. So coming to the trace operator gives the sum of the diagonal matrix for the entries of a matrix. Just a trace operator is just a sum of all the diagonal elements. And you can also get the Frobenius norm using the trace of a matrix times its transpose. And trace of a matrix, of course, when you do the transpose of a matrix, the trace does not change. And apparently the trace of a matrix is commutative, or so the you can trace of ABC equals to CAB or BCA. So this is the generalization of that. It's commutative determinant. Let's go to example principal component analysis. So basically, PCA is basically data compression. So you take like a three. Now, if I try to explain PCA like in a simple way, so basically the main idea is data compression. So you take three different, let's say, like we have a table of values. Let's say, like a city and population and GDP and literacy rate and everything like that. So we have a whole thing like that. Now, if you want to turn this into a graph, so that we want to visualize it or try to process it or in any ways, you try to when you try to convert it into, I mean, we cannot possibly see like multi-dimensional graphs, and it's also very difficult to calculate it anyway. So we'll only do like a three-dimensional graph here. So what PCA helps us to do is you can compress a few of the columns that I've said, like you can compress the population literacy rate and let's say another value called another column with the length of road and length of railways like that. So you can compress all them into one column. Let's say we can call it like a column of X factor. Let's say X factor. X factor. So and this helps us to visualize the whole data in a lesser dimensional graph. So now you can plot the countries like in the x-axis and the x factor in the y-axis, and let's say on the z-axis you can take the area of the country, let's say. So now we have a table which has like around 10 columns compressed into a graph of just 3 dimensions, and now it's just much easier to visualize this and understand this. It's also much easier to process this. So that's how we try to do the principal component analysis. And PCI is equal to the eigenvectors of the covariance matrix. So that's the technical definition of it. What I explained just now is the overview or the raw explanation of it. So we will skip all these technical derivations and explanations here. So yeah, like I said, this is the explanation. So it's there is countries and GDP, happiness, population one, okay, population one and property 1, property 2. You can combine the GDP and happiness into one, population and the property 1 into this attribute called 2, and property 2 and more into another property called 3. And you can visualize all them like much easily by compressing them. So it's basically a way to compress the data, and we call it principle because uh, the things are compressed into one main thing. So yeah. So we have finished just the linear algebra chapter. We have finished skimming through it. So now let's try to skim the chapter probability and information theory. So now probability theory is a mathematical phenomenon for probability theory just provides means of quantifying certainty and axioms for deriving new uncertain statements. So it provides a means of quantifying uncertainty. So we have a lot of uncertainty in this world. It provides means of quantifying those uncertainties. So trying to hold them, what is uncertain, and axioms for it also provides axioms for deriving new uncertain statements. So just like a PCA, you can combine uncertainties into new uncertainties. In artificial intelligence applications, we use probability theory in two major ways. First, the loss of probability tells us how AI systems should reason. So we design our algorithms to compute or approximate various expressions desired using probability theory. Second, we use probability and statistics to theoretically analyze the behavior of proposed AI systems. So how AI should reason and work. We use it with probability there also, and we also use it to analyze how these proposed AI systems have behaved. So that's about that. And why to study probability anyway? So inherently, there's an inherent stochasticity in the systems being modeled. So these are the three possible sources of uncertainty. The most interpretations of quantum mechanics describe dynamics of subatomic particles as being probabilistic. So when you go to the quantum level, things are not discrete or exact. So things are rather confusing. The only way to be sure about anything is there's just no way to be sure about anything. So the only way to deal with the things at quantum level is to assign probability to the things. Can also create theoretical scenarios that we postulate random dynamics such as the hypothetical card game. So inherent stochasticity is why we need probability, and also incomplete observability. In a lot of areas, especially in AI and in machine learning and all, where we deal with huge amount of data, there's just no way to um, analyze them or predict what can happen next with certainty. So there's incomplete observability factor there. Also the incomplete modeling. So we don't have the exact modeling of how those things work as well. So that's why we need. So here we have, so here we will just go through them in a way which is which just helps us to understand the concept. So we're just trying to um, understand the basic elements here. This is just a revision, and explaining continuous variables, random variables, probability density functions, marginal probability. So this is marginal probability, as you can see. Marginal probability on paper when you're in a grid with different rows and columns. It's natural to assume a grade, right? Yes, madam. Just conditional probability is denote conditional probability y given like this. So this is the formula for conditional probability. Probability of A given B has happened is equal to probability of both A and B happening divided by the probability of B happening. So there's chain rule as well of conditional probabilities, as you can see, and this is how we find them. Correlation is the relation between two variables. So this is the expected value. Covariance is the measure of correlation. So what's the difference between correlation and covariance? Uh, just because this concept has been brought up. So covariance is the measure of correlation. Correlation is just the relation between two quantities, and covariance is how correlation has changed. So covariance is the degree by which variable changes with the relation to each other. Okay, so the degree, and this is just a relation, the degree by which this relation has changed. And coming to common probability distributions, so here we have a lot of concepts. So now for just to summarize, when the for the task of when data is like smooth and infinite, you use the Gaussian distribution. The data is like binary. When you're dealing with binary uh, data, you use the Bernoulli distribution. And when data is like multi-class, you use multinull distribution, also called as categorical distribution or k-nary or k-stage distribution. So this is like the overview summary of this. So again, just to study it again, Bernoulli distribution is for two states. When there are two states and the data is binary, also called as binomial. And when there are k states, when there are multiple states, we call it as a multinull distribution or categorical or multinomial distribution. And when the data is smooth, we have to deal with the infinite states, then we use the Gaussian distribution. So they have also gone into central limit theorem and multivariate normal distribution, which I shall go into them in the separate videos as I said. Coming to Laplace distribution, so difference between two exponentials. So Laplace distribution is just difference between two exponentials and the Dirac. So this is how a Laplace distribution would look like. And the Dirac, you might have heard this from the Paul Dirac cones and from quantum mechanics. So Dirac distribution would look like this, and the empirical distribution would look like this. And yeah. So the Bernoulli is a simple, and binomial is when there is mixture of them. Categorical is for simple, and multinomial is a mixture of the exponential distribution. You use Laplace, and when things are empirical, you use the Dirac distribution. You have seen one example of mixture distribution, empirical distribution. Component example. So what's a latent variable? So the mixture briefly claims the concept, which will have paramount importance later. So what exactly is a latent variable? A latent variable is a random variable that we cannot observe directly. The component identity variable mixture model provides an example. So now it's possible to describe PFX without reference to the latent variable because it's latent. So it's just a hidden variable, which what the latent variable is. And so we have come to Bayes rule. They are the sigmoid functions, and we will come to these various types of sigmoid and soft plus functions once again later on. And so this is about technical details of continuous variables. Sufficient to understand the intuition that the set of measure zero occupies no volume in the space that we're measuring. So there is almost everywhere. So this is a useful term for measure theory. Property that holds almost everywhere holds throughout all space except for a set of measure zero. So a probability of x lying in an infinitesimally small region with volume of sigma x is given by p of x sigma x, and yeah, we use Jacobian matrix here. So now we have come to information theory. Um, so we mostly use a few key ideas from information theory to characterize probability distributions to quantify similarity between probability distributions. For more detailed information theory, see this textbook. So the basic intuition behind information theory is that learning is an unlikely event that has occurred. The more information than it is a likely event has occurred. Okay. So this is the basic idea. So again, this is a basic idea of information theory. I don't know how to start. So basic idea is that learning that an unlikely event has occurred is more informative than learning that an likely event has occurred. So basically, in information theory, you're not looking at things like the sun has risen. That's not information. I mean, that's a given. So, so when you're told to collect information about a village, let's say, and you're sent there, let's say that you are information collector or scientist. If you write down things like the sun has risen, they are eating food, and they're sleeping at night, that's really not information, is it? So the information is something that is not likely. So that's something that is not known by default, or something which is abnormal, something which is new. So the basic intuition behind information theory is again is that an unlikely event has occurred. Okay. Learning that an unlikely event has occurred is more informative than learning that a likely event has occurred. So the information of something with more entropy is higher than the information of something which has lesser entropy. Okay, let me write that down. So information of something of more entropy is more than information of something of lesser entropy. So entropy is again a basic concept. I hope you are already aware of that. And so we would try to quantify information in a way that formalizes the intuition. So likely events should have should have low information content. And in the extreme case, events that are guaranteed to happen should have no information content whatsoever. So the information of sun rising is basically zero in that sense. Less likely events should have high information content. So like I said, independent events should have additive information. So yeah, so independent events should have additive information. This is another concept. For example, finding out that is a toxic coin has come up as a heads twice should convey twice as much information as finding out that a toxic coin has come up as heads once. So one net is the amount of information gained by observing an event of probability 1 by E, where E is the constant, the famous constant. Other text is based on algorithms called bits or Shannons. Information measured in bits is just the rescaling of information measured in nets. So we're using natural logarithm with the base E. Our definition of I of x is therefore written in units of nets. One net is the amount of information gained by observing an event of probability 1 by E. So when you observe an event of probability 1 by E, you have gained one net of information. Self-information deals with uncertain outcome. We can quantify the amount of uncertainty in an entire probability distribution using Shannon entropy. So the Shannon entropy of distribution is the expected amount of information in an event drawn from the distribution. Shannon entropy, the distribution of a distribution, is expected amount of information. So remember that expected amount of information in an event drawn from the distribution. Often in an event drawn from the distribution, it gives a lower bound on the number of bits the logarithm is based to, otherwise the units are different, needed on an average to encode the symbols. drawn from distribution P. Distributions that are nearly deterministic, where the outcome is certain, have lower entropy. Distributions that are closer to uniform, have higher entropy. When X is continuous, an entropy is known as the differential entropy. So if we have two separate probabilistic distributions P of X and K of X over the same random variable X, then we can measure how different these two distributions are using the Kullback-Leibler divergence. Yeah, so if you have two separate probability distributions over the same random variable, okay, this is important. So over the same random variable, two separate probability distributions P of X and Q of X over the same random variable X, we can measure how different these distributions are using the Kullback-Leibler divergence. So this is how we measure the Kullback-Leibler divergence. So basically trying to find the difference between those two separate probability distributions in order the same random variable. How different is in this divergence? I mean, basically this is an entropy. So let's see. So in case of discrete variables, it's the extra amount of information measured bits. The machine learning usually the nets and natural algorithm. So K divergence is a non-negative and measures difference between two distributions. It's often conceptualized as measure some sort of distance between the distributions. However, it's not a true distance measure because it's not symmetric. So it's not like the callback divergence of P from P minus Q is equal to Q minus P. So it's not equal to that. So structured probabilistic models, let's go through that. We can greatly reduce the cost of representative distribution if we're able to find factorization into distributions for fewer variables. Yes, that's that. Keep in mind that these graphical representations of factorization are a language for describing probabilistic distributions. They are not mutually exclusive families of probabilistic distributions. Being directed or undirected is not property of probability distribution. It is property of particular distribution of probability distribution. But any probability distributions may be described in both ways. Yeah. So there's that. So for directed models and undirected models, they're just talking about this. And can be described both ways. Again, probability can be described both ways. And so we will end here and we'll continue with the chapter 4 from the next one.